Hello everybody, today I'm going to talk about parametric robustness analysis for LTI systems. And here basically the red system represented by the red lines is the system that we'll be focusing on today. And we are going to do parametric robustness analysis. What does it mean? We have two parameters for this problem, right? And this is an LTI system, and we know for which values P1 and P take can take on, right? Basically, for example, P1 might be a resistor, P2 might be an inductance value or something, right? And we know P1 and their P1 can take some minimum value and P1 takes some maximum value, right? We know that range basically, and it's for the P2 as well. And we want to know, for example, first of all, the ideal case would be this: is the system stable for every values of those parameters that they probably can take on, right? And this is probably the first question, and I would assume it would be no. And after that, okay, then what is the duration that we can tolerate, right? We have some minimum and maximum values for P1. However, in real life, P1 can take that minimum and can take that P1 maximum values, right? Can take some values between them. However, our system might, for example, be only stable for P1 min star and P2 P1 max star, right? Okay, and we would like to know that. Let me just make it bigger. We would like to know that range, and again for the P2 as well. Another version of this problem is to, hey, find me the P1 values, right? P1 like under bar, right? And P1 upper bar and P2 as well, right? P2 under bar and P2 upper bar, meaning minimum and maximum. This kind of notation that some books use often. And find me those values such that we have some A matrix, right? We have some x dot equals A, and A depends on P1 and P2 basically, times x. We want to know, or we want to determine these durations range. That will be correct. We like to compute those ranges, parameter ranges, such that A is Hurwitz basically, right? And I want to say this P1 comma P2 is going on. Okay, let me just make it. Can we not do that? Okay, is Hurwitz, right? Hurwitz means all of its IM values twice in the left half plane, open left half plane, right? And we like to impose that type of constraint. Okay, and alright, before saying anything, by the way, let me talk about today's agenda. I mean, we will do two basic tasks, right? And we will use MATLAB and YALMIP optimization toolboxes. Okay, and then I'm looking at this. Yeah, the first task is to generate this plot. And what is this plot? This is the plot, right? Parameter space basically, and thankfully there are only two parameters, so we could visualize, right, that type of object, geometric object. And by computing, right, generate this plot by computing the P1, P2 values, right, such that this A matrix is stable, or the dynamical system is stable basically. Okay, and how we would do that? We will do, I mean, we can do, for example, we would, for example, P1 and P2, right, and these are the parameter ranges, right, and we will basically randomly sample from that parameter space, and let's say we get like 100 points in that parameter space, and for every, I'm gonna say pi, right, for every pi, just check the stability for I equals 1 dot dot 1 and 100, for example, right, and pi, and then compute a pi, and then check if API A of pi is stable. I'm gonna call h dot service, okay, all right, and if yes, right, store that value, right. I was going to say record, but okay, store it. Okay, the parameter, store the pi basically, right, pi. Okay, and that's it basically. Even I don't need this, and okay, this is the basic pseudo MATLAB code, right. Let me get this. Okay, this is going to be the rational, and we will just apply this strategy in first task, right, and I would like to actually delete that, but okay, before saying anything, right, and let me say, I'm thinking about whether I should do the first task on MATLAB right away, or talk about the second task. I'm thinking, and okay, let's talk about the second task, right. Okay, what is the second task? It basically says check the quadratic stability for the given, right here. This is very small. Let me zoom in, right. Okay, for the given P1, P2, and P1 times P2. Why I say that? Because here we can see we have P1 and P2, but also P1 and P2 also appears in this type of nonlinear form, right? And as you might imagine, we will going to do, I mean, we will do something like this. We have P1, right, appearing by itself, and we have P2, and we also have P1 times P2, right? And we will call this term basically P3, and then act like we have three parameters uncertain, right? They take on some values in the given ranges, and we will check the stability in that case, okay, because it would be better, it would be easier, and we have the tools to handle with that type of situation. Otherwise, yeah, it would be harder, maybe impossible. I'm not 100% familiar with that subject. And okay, let's see the, let me get the red color. Let's see the range. The nominal value is 3 here, but plus minus 0.2, right? Okay, and this is the case here, come on, okay, right, nominal plus the deviation, right? And deviation point is 0.2 in this case, and nominal value is 7 and the deviation is 0.5. Okay, and here this I would like to say P3 at this point, right? And P3 parameter takes as minimum value basically P1 P3 minimum equals P1 minimum times P2 minimum, and P3 maximum equals P1 maximum times P2 maximum, right? Basically, since they are, positive numbers. Okay, and it would be not the case if they were like negative, and we would, in that case, we would look at all the permutations, right, or the combinations. And okay, did I mention the references? I guess I didn't. Okay, and there are, let me get another color. Okay, there is a Matthew Peet video on LMI control, and I link again will be in the description down below. And Duan Yu book on LMIs in control systems, right? And the example is from this book, Lecture Notes in Control and Information Sciences, and 320, right? And sorry, 312. And the name of the book is Positive Polynomials in Control, D. Henrion and A. Right? This person, editors, these are editors, and from page 283, and from section 3.2, and the name of the section is Parametric Robustness Analysis. Okay, and all of those will be in the description. I just want to state references. Okay, and I'm looking at this. Yes, that is the alright. I was talking about the quadratic stability, and quadratic stability is, I'm looking at this. Okay, and first of all, let's recall what stability is for LTI. Right? Stability for LTI. The problem is given, right? Theorem. There exists a P, symmetric P, which is positive, such that a, sometimes it is written EA symmetric negative, right? And this notation means, just for example, right, this notation means x plus x transpose. Okay, so okay, let me also give this the form everybody is familiar with: A transpose P plus PA being negative. Okay, and this condition basically is like v of x being positive, right? But in this case, polar x in, right, Rn minus excluding the equilibrium point, right? And here this condition basically is like v dot of x being negative, again for same domain, right? Rn excluding the 0, right? Okay, this is the stability and for LTI. For this, let's check this. Okay, yes, this is the stability. And what is quadratic stability? And actually, before saying quadratic stability, let me say one thing: robust stability, right? Robust stability, and robust stability is this: you have, for example, A of P, only one parameter. Okay, let's say, and P takes on values between P minimum and P maximum, right? Or T lower and T, or upper, right? And okay, but here is the catch. Here is the assumption: P is a parameter, but it is known to be a static term, meaning, okay, we don't know what P is, basically. We only know the range, right? Let's say between 3 and 5. Okay. However, it is a it is constant. It is static. If, let's say, 3 and 4, right? Let's say it is 3.2. But it will be 3.2 from the beginning of the operation and from the end of the operation, right? Till the end of the operation. So it is not, for example, P is not something like this. 3 and 4, right? P is not something like this, basically, right? It is not like that. It is just a static term, alright? And in that type of cases, you can use robust stability, okay? However, only in that case you would use robust stability, right? Because if you think, for example, P is static and it is not, and you only prove the closed-loop stability in that way, you only prove the robust stability, right? I mean, your closed-loop might get unstable during the operation, and if P is not static, right? For example, it is like it depends on temperature or something, right? It takes between 3 and 5, but as temperature increases, so does P, let's say. In that case, yeah, you wouldn't want to have only robust stability proved. Yes, okay. Yeah, let me give the definition. P is, I mean, I don't want to say P actually. It will be confusing. 1 sec. Okay, let me just check this. Okay, well, here is the definition. I'm going to get another color, right? Here, the definition. The pair A plus delta, right? And delta is a normal delta, but here this is like the bold delta, okay? And this delta is basically a number, let's say, but this delta, capital delta, is a set, okay? All right. For example, let's say delta 1 and delta 2, and this set is this delta, right? And every point is nominal delta, okay? And let me get rid of this, and here is the definition. The pair, this pair, and this is the type of notation where we have A, but A is parameterized by some parameter, right? And each parameter, right? And each parameter takes a value between some pi sub, pi lower, and pi upper, right? Okay, and in that case, all right. Okay, this expression, this linear dynamical system, let's call it parameter dependent. Yeah, that will be better. Parameter dependent, or uncertainty including, right? And possessing uncertainty possessing linear dynamical system is robust stable over this parameter space, right, over this parameter space, you have two options. You may consider that as a parameter, or you may also consider that, hey, parameters has some nominal value, but that uncertainty we have also, right, occurring in the linear dynamical system, and you can either see this as a parameter or uncertainty. Okay, that's the two way of thinking about it, I guess. And okay, is robust stable over this parameter space. All right. Yes, if for every parameter, right, e1, e2, right, let's call this, and this is like a perfect rectangle. All right, this is e1 min, and this is p1 max. Okay, here this is p2 min, and here this is p2 max. Okay, I should make that better. p2 min and p2 max. Okay, here this is the parameter space basically, and in a way we are searching for a p, or we are searching for infinite number of p's, and that corresponds to, okay, there are infinite cases. Okay, right, let's say this is case 1, and this is case 2, and this is case 3, and dot dot dot, and this is case infinity. Okay, right, for that case we have some a value, right, a matrix, okay, state matrix, and then we will find a p. This is for I equals 1. Okay, we will find a p for that given numerical a, and this is I equals 1. Okay, right, and for that again parameter value, or yeah, in the parameter space, right, there will be, of course, since this is a continuous thing, right, there will be infinite, and I'm making a hand wavy argument right now. Okay, and a I equals 2, right, we have this is a numerical matrix, right, and for that we will compute some p, right, p matrix, Lyapunov matrix, I equals 2. Okay, all right, and for seconds, okay, all right, and here this is again we have a equals 3, right, and for that we will find a p equals p sub I equals 3. All right, dot dot dot, and p infinity, a infinity. Okay, this is the kind of general idea. Okay, however normally you will do that, right? No, normally you will do that, or you would have to do that. However, since you have let me write this polytopic parameter space, or I'm gonna call it uncertainty. Okay, since you have some polytopic uncertainty, all right, what does it mean? It means, for example, in 2-dimension it looks like this, right? It looks like this basically. For example, okay, in 2-dimension. All right, let's check what would happen in 3-dimension. All right, oh, it's going to be really hard plot for me. Okay, for example, this is another polytopic, right, that type of thing. All right, meaning, for example, in this case, let's call it p1, p2, and p3. In this case, P1, P2, P3, right? We have some P1 minimum and P1 maximum, and P2 minimum and P2 maximum, and P3 minimum and P3 maximum. This is like the general idea, right? For example, let me write this also. This is cube, right? But hypercube, for example, let's say we have 10 parameters, right? Let me delete all of them. Okay. Let's say we have P1, P2, P10, right? P10, and for every one of them, we have some minimum and we have some maximum. For P2, we have some minimum and we have some maximum, right? Again, same goes for the 10th term, right? Okay, this type of parameter or uncertainty representation is called polytopic uncertainty. Okay, and also it doesn't have to be like a cubic geometric object, right? For example, it can also be something like this: P1, P2, and P3. Something. Okay, get another color, right? Okay. This one and this one. Okay. For example, Matthew Peet explains that well, and for example, this type of representation, for example, right? It kind of, when you see that, you will directly think, hey, that means P1 and P2 doesn't depend on P5, or every term is decoupled from other terms, right? There's, for example, you make P1 values, P2, you have some, I don't know, some object, okay, some object that you control, that plant, right? Plant, and plant has P1 and P2 parameters, right? And you produce that plant. For example, let's say, call it an electric motor, okay? You produce like 1,000 electrical motors from the manufacturing line, right? And you measure each one of those electrical motors, right? Their P1 values and P2 values, and you measured it and plot it, okay? You measured it and plot it. You measured it and plot it. If you see something like this, that will mean there's some type of a correlation between them, right? Okay, for example, as P1 increases, so does P2, right? And in that case, you shouldn't say P1 takes minimum and maximum values and P2 takes minimum and maximum values. You would do basically polytopic uncertainty thing, and this is another way of looking at it, okay? And hopefully in the next videos I'll be talking about that as well. I'll be covering up this subject as well. And okay, so this case is valid only when all of the parameters are decoupled. They are not related. They don't affect each other, okay? Alright. For example, let's consider this case. There is some type of correlation between all of them, right? It is almost like some type of, for example, P1 constant times P1 and constant times P2 less than some constant. That type of constraints are imposed. It's almost like that, right? Okay. Because, for example, how would you mathematically describe that volume? Let's think about that for a second. For example, this is, and let's call it A, okay, and this is 0, right? A, right? Okay. So first of all, each one of those takes values between 0 and A, okay? Alright. And only having this constraint kind of means A, right? We have this P1, P2, P3, right? We have this object, cube, basically, right? Alright, but our object, it is not a cube, right? It is smaller than that. And if we, for example, if we try to prove the stability for that case, we maybe fail. We may fail, or if we don't fail, our controller, let's say, okay, it would also mean that our controller is over conservative, right? And if your controller, if you constrain that much, right? If you design your controller that such that it is able to handle with that type of uncertainty to a point where it doesn't need to, right? You kinda, it's a trade-off, right? You kinda sacrifice some type of, how should I say? Yeah, sacrifice some performance that you would get otherwise, right? And basically, the whole story is this trade. The trade-off can be explained like this, right? Robustness, right? And performance, right? So if you design your controller such that it is very robust, it is over conservative, right? And you will sacrifice some performance, and you might, it depends on, also it depends on your, how should I say, it depends on your application as well, right? Maybe the robustness is very important at the moment, and there are some cases where it is not. Yeah, it depends on the application. So okay, that was a big tangent. Okay, and okay, first this is the constraint, right? And after that, okay, here in this case, for example, let's think about this case. You have P1 and P2, right? And your area of interest is this area, right? And 0, right? And let's not care so much about the specific values, right? Let's consider the boxes as some given coefficient, right? And okay, how would you describe that area? But first of all, describe that P1 and P2. Let's say these two boxes, same, right? Same value, and this is 1. And also, you would probably have, right? You would also have some constant times P1 plus some constant times P2 less than some constant, right? Okay, so there is a word for that, and it is affine constraint, right? Okay, and I just want to make that clear. And also let's focus on the other our original problem, right? We are interested in this mathematical object, and in that case, you will have some constant times p1 plus some constant times p2, right? Plus some constant times p3 less than again some constant. Again, affine constraint, right? Okay, and alright, it is not only box constraints where we have p1 greater than some value and is sandwiched between two values, right? And also same goes for p2 and other parameters, right? But we have also some affine constraint, okay? And hypercube also a polytop, right? Okay. So polytopic uncertainty also includes hypercube, but hypercube is a specific case of a polytopic uncertainty, right? And okay, so where were we? Yes, we were here in this case. Do I delete that? No, I shouldn't. Okay, let me get red color here, and this notation is very important. It says, right? Says that for all parameters there exists a p, right? Or let's read it like this: for every parameter. Okay, let's say I sampled. Let me get blue, right? I sampled a parameter, right? I just sampled it. Let's say we have infinity. Okay, I mean it's infinite, but let's say we have infinite. Okay, let's consider infinite as 1000 or something, right? A number that we can handle with, and we have infinite number of parameters, right? From this space, from this set, and okay, starting from one, we just sample one, right? And we iterate over that set, and for that value, for that parameter value, we have a corresponding state matrix, right? We have a corresponding linear time invariant system, right? Okay, and for that matrix, state matrix, you will find a p value. Okay, and same goes for other values, other parameter values. Okay, again, iterate over this, right? Parameter sets, you have some parameter value, right? And for that parameter value, you generated, or there is some a that corresponds to that parameter, right? And for that a state matrix, you will generate, or you will solve that feasibility problem and generate and compute p, right? And you go to infinity. Okay, and first of all, this is impossible. You cannot do infinite number of computations, and for that case you don't need to do infinite number of computations. You only prove 1, 2, 3, 4. You only prove not infinitely long, right? Infinite large. You only prove finite cases. Okay, right? And here the finite cases is this: you have, okay, I'm only talking about in this video is only related to hypercube case, right? Cube, right? Okay, let's say we have starting from 1, okay, and 2 and 3. Okay, we have 3 parameters, and we will have 3 parameters actually, and we have 3 parameters. All right, you will have, right, you will have p1 min, p1 max. You will have p2 min, p2 max. You will also have p3 min and p3 max. You know these numerical values, right? Okay, and basically you need to prove in that case 2 to the number of 3, 2 to the 3, right? 8. Okay, you need to prove 8 cases. You will basically, for robust stability problem, you will find 8 different, it's probably different, 8 different p-values. Okay, right. Actually, robust stability is something to a good point to start this subject, I guess, right? Okay, and all right, E1 min. You know what I should do? Okay, just I'm thinking about this. There are 3 cases, right? Okay, why? Because 2 cases for that from that parameter, 2 cases and 2 cases, 2 times 2 times 2 equals, right? Okay, and we need to prove 8. Okay, and thinking about this, E1 min, E2 min, E3 min, right? And E1 max, E2 min, E3 min. I guess you know what I'm doing right now. Okay, E1 min, E2 max, E3 min, and there will be 8 cases, right? And the final cases is E1 max, E2 max, E3 max. Okay, 1 2 3 dot 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 8. Okay, for that you will have some, since you have A, P1, P2, P3, right? You have some A value, right? And for that A value you will find a P matrix in, right? Okay, I'm very sloppy with my writing today. And okay, you will have 8 different parameters. Okay, this is basically robust stability in a nutshell. Maybe not so nutshell, but all right. And here I also like to mention for this notation, for delta in that, right? Let's check that again, right? There exists P, right? Such that dot dot dot, right? After that the theorem is stated. This notation, and let me circle it, right? Follows and there exists. If there exists comes after for all, right? For every, it means that P basically is depending on the previous value, right? Okay, and this is a good subject actually. For example, you see that kind of a notation, and for in the theorems. Okay, for example, let's say we have some theorem, all right, and there is a statement in that theorem for delta 1 in the set, comma, for delta 2 in this set. Okay, there exists P. In that case, that P would be depending on, right, delta 1 and delta 2. Basically, you can consider that P as a function of delta 1 and delta 2, right? However, and this is the crucial part, if we switch those atomic terms, right? We switch those terms, there exists P over delta, right? In that case, there is only one P that satisfies the constraint, and such that there will be some constraints, right? There is only one P that satisfies these constraints for every delta, right? Meaning in the robust stability, okay, let's check that. In the robust stability, let me write that again. Robust stability. Oh my, wait a sec. Okay, again, worse, but right. We have determined basically, right? Or we need to determine 8 P matrices, right? P matrices. However, for the quadratic stability case, we only need to find one P, only one P that is valid for every one of those cases, right? Alright. We need to find the P value for the quadratic stability, and that P value needs to satisfy all of those cases, and here's the important word, simultaneously, right? And that's why quadratic stability is a harder problem. I mean, when I say harder, I am saying basically, for example, your, okay, it is, since we are at this point, quadratic stability, right? Quadratic stability implies robust stability, right? However, robust stability doesn't imply, converse is not correct, okay? Robust stability doesn't imply quadratic stability, okay? And another important point is that, and you might be thinking, so what's the benefit of quadratic stability? Robust stability is only helpful if you 100% sure that your parameters doesn't change with time. It is like, okay, that P1 value is 5, or it takes a value between 3 and 5, and it takes 4, for example, and it is only 4. It doesn't change, right? Okay. Alright. However, quadratic stability have the ability, for example, we have P1, right? And here P1 boundaries, right? P1 ranges, and one sec. Well, okay. Quadratic stability again implies robust stability, but converse is not correct. Okay. Alright. It is not an if and only if condition, right? It is not a necessary and sufficient condition, right? And alright, here I would also like to say that robust stability, yeah. Another point, for example, P implies Q, right? Okay, here we can say that P is a sufficient condition for Q. Okay, P is a sufficient condition for Q, right? And also Q is a necessary condition for P. Okay, I'd also like to make that clear. All right. However, if you also have P, like if and only if, right, then P is a necessary and sufficient condition for Q, and Q is a necessary and sufficient condition for P. We would also like to say that. And okay, right, I'm looking at this. Yeah, another thing. For example, E, right? Here this is E1, E1, E1. Okay, takes values between 3 and 5, for example, right? Maybe 6. Okay, and it is like that, right? It it is basically time varying signal or time varying parameter, right? Okay. For example, you have 1, 2, 5 and E1, and E1 is a time varying parameter. In that case, you would like to have quadratic stability, right? Okay. All right. I'm looking at this. Okay, I'm looking at my notes. Right. That was a long tangent, but I guess I'm looking at this, and we should also give the definition for quadratic stability, right? Okay, copy. Okay, paste. All right, this was the robust stability. Here, definition, and the pair, again the same notation, right? This is a set, capital data, right? Is quadratically stable over capital data, right? If, and here's the catch, there exists a P, right? There exists a P such that I mean, we can also say, okay, I wanted to make that point clear. For every delta in that set such that P is positive and A plus delta transpose times P. Remember, it is like this, right? Now recall. Okay. Plus P times A plus delta less than 0. Okay. It's negative, alright? And we only switch those two terms, right? Okay. And this is quadratic stability and this is robust stability. Alright, we'll be focusing on quadratic stability because it's, you know, the important case actually. And alright, what was the problem? The origin of problem. Origin of problem is this. And you know what? We also need to complete the task 1, right? Before saying more about that, it's kind of not edited well, I will say, right? This lecture is, and let's focus on the first task. Okay. Now we are focusing on the task 1, right? Here, this is the parameters and ranges, right? Their respective ranges, and I'm going to basically create E1 vector, right? And using MATLAB linspace, I'm just explaining the pseudocode here, right? 0, 9, and let's say 100, right? 100 would be really large, but let's say 100, okay? And after that, E2 vec, right? Again, linear spacing, right? 2, and it takes between, or it discretizes the range of 2 to 10, right? To 100 basically gives you an array of 100 numbers. Okay, equally spaced, right? Okay, all right, and we just iterate over, right? I mean, since we have two vectors, okay, I'm gonna call it iterate over e1, e2, right? Terms, all right, and for each e1, e2, all right, generate a star, right? A star, and for that a star, for that specific numerical A matrix, right? Solve, okay, solve the feasibility problem. What is the feasibility problem? Find P, right, such that A, let me write this, A star, or I'm gonna use shorthand notation, right? Okay, just solve this feasibility problem, right? Okay, this is the, and if feasible, right, store it, store e1, e2 values, and yeah, that is the code. And now we are going to MATLAB. Let me open it up. Okay, device capture device. Okay, now we are here, and I'm looking at the code, right? First of all, this is only for SDP solver, SDPT3, and for YALMIP, right? Just ignore that. Okay. Yes. Let me run that, and let me run that. And after that, let's. This is wrong. Okay. YALMIP. I should say YALMIP robust parameters are better robustness analysis, right? Okay. And here, let's only consider. Okay, this is our A matrix. Okay, you can check it. And this is our A matrix, right? Let's only consider for a specific given P1 and P2 values. Let's remember that case, okay, first of all. And after that, go step by step, right? And question, does there exist a, this is a feasibility problem, P, Lyapunov matrix, positive, such that the given condition holds, right? Okay. And here, this is for numerical accuracy, right? Again, we are defining some YALMIP variables, okay? And 3 by 3 symmetric, okay? And here, this is the first constraint, P being positive, right? And this is the second constraint, this term, or V dot variated term, being negative, right? Okay. And I'm also looking at this, and here I'm just stating which SDP solver to use, right? Okay, optimize function. The structure is this: optimize. First argument is the constraints, right? And second, objective. For example, we don't have any objective. This is only a feasibility optimization problem, right? Okay, and options, and here the options, okay. And after that, we check the solution information. for example, if it is infeasible, right, or it converge to the, you know, optimum value or something, right? We like to get that information. Okay, so this is like 10 lines of code. Okay, so not too bad. Okay, let's run it, right? Let's run it. Okay, what does it say? It say successful sort, right? Okay, and here using this line we get our solution, right? Here again, let's print that. Okay, here that must be positive, right? That matrix must be positive, so its minimum eigenvalue must be positive, right? And it's positive, right? And that matrix v dot rated term must be negative definite, and that's why its eigenvalues are, you know, negative, right? Okay, and it is okay. And you know what, if you like to do something like this, I'm gonna, for example, what is our p? It has some values larger than 50, right? Let's say if you don't like to see that type of cases, right? Let's say minus, and do we have minus? Yeah, we have. For example, let's check minus 10, right? Minus 10. I vectorize the p matrix, right? And 10. I'm saying I don't want any p values, also the p matrix entries outside of this range, right, that I specified. And I just basically added one more constraint, right? And this is a linear constraint, so it's not, you know, something that we need to worry about. But we may not get a solution, by the way, right? I just want to try that if it is possible for me to get a, you know, p matrix such that these constraints are satisfied. Okay, let's run it. Okay, it gives me, right, another p value such that the entries are in that range, right? Okay, and all right, I just want to, you know, mention that you can add another constraints. For example, you may add other constraints such that you like to, for example, promote sparsity. You don't like p matrix to be full matrix, right? But you like to your p matrix to be having, you know, only a couple of non-zero terms, for example, right? Okay. Okay, this was the, you know, general of LTI stability. We talked about that before. I just want to, you know, quickly mention, maybe not quickly, but okay. And yeah, now we are going to generate that plot. All right. It is again really easy, right? Discretization numbers. All right. I just space get the values in p1 vector. I called it, right. Get the p1 values between the valid range, right? It was mentioned before, right? And between 0 and 9, and give me 20 values, right? Linear space in that range. And again, same for the p2, and this is, I mentioned that already, right? Okay, and I call it blue dot locations. Blue dot locations basically will have p1 and p2 values such that the LTI system is stable, right? Okay, here, for example, I could also do that, right? And here you can see 1 2 3 4 5 6 7. Okay, just these lines, right? I just, you know, copy and paste, right? Okay, I just want to, you know, make that clear. All right, let me write it outside of the for loop. For loop is already slow as is, right? Okay, we are here. We have, since we have two parameters, right? We have two for loops, right? We are iterating in that parameter array. All right, and we are assigning that. Okay, and this is basically our A matrix. I just substituted P1 and P2 terms, right? And the numerical accuracy constraint definition here, v of x constraint, v dot of x constraint, basically. All right, solvable option and optimization. All right, and after that, if solve that problem equals 1, that is, for example, you get solve object, right? If you solve that, you assign the solution to some number, right? Some object, I should say. And this object has a couple of fields, and one of them is problem. And problem basically gives you this. If you have it takes numbers, right, integers, for example, and there are a couple of cases, different cases, and 1 signifies infeasibility. All right, and if it is right, it is 1, right, that means infeasible. We don't care about that case. But if it is not infeasible, meaning it is feasible, by the way, there are only 2 cases for that problem, right? Okay, and just store that location, P1 and P2 values, basically. Okay, and here I just plot every one of them, right? Okay, let's, yeah, this is it. Okay, let me get that, and I use tick and talk to check it. I guess we will have, let me run it for 10 values. Okay, all right, I'm looking at this 100 problem, 100 separate problem, basically, right? Maybe yeah. Okay, let me get the, okay, this is it, right? Okay, now I'm going to look for other cases. Let's make it, no, 220 is already. I'm gonna make it 30. Okay, and I'm going to pause here. After 88 seconds, right, we basically generated this plot, and here we can see the parameter values. For example, for this given parameter value, our system is stable, right? Okay, and this plot basically signifies this. And of course, this is an example for a system, even a small system with a couple of parameters. You wouldn't do that, I guess. Maybe just for the fun of it or for learning purposes. Okay, and all right. So from that, I guess, right, we can say 3 and 7, right? 3 and 7 is like the safest area, right? If you don't like to go to that area, right? 3 and 7 is nominal value, right? And now we are going to prove the quadratic stability where our nominal value 3 and 7, right? And again, for hypercube, right, 3 minus the deviation will be 0.2, and for P2 the deviation will be 0.5. 7 plus minus 0.5, right? We will look at that rectangular region. Okay, all right, I'm now going to just mention or go step by step about, okay, wait a sec, yeah, task 2. Okay, this is task 2, prove quadratic stability for a given parameter intervals, right? Parameter, I can see that intervals. Okay, all right, yeah, for that I need to explain a couple of things, right? Let me get this. Control home. Alright. Okay. Here we again. We need to. Here we are in the second task. Okay. And this is our linear system. This is our linear system. And we have these three parameters. Actually, we have. Let me correct that. We have two parameters, P1 and P2. However, here, if we look at the 3, 3 and 3, right? And we see that they are nonlinear, right? And this type of term is not something we have the tools to, deal with, other than for the simple cases at least, right? And we have, other than to reparameterize it or rename it, and I just rename that calling P3, right? Okay, so these are the values that are given to us. All right. Okay, for example, here in this case the nominal value is 3 and the deviation is 0.2, right? For example, E1 is 3 plus or minus 2, right? And we will use something like this, right, where delta is takes some value between 0 and 1, right? Okay, there are a couple of things, and there are a couple of ways of representing the same uncertainty. Okay, and here again we have those two parameters, and I just called E1 times E2 E3, right? I just rename that. Okay, and again we need to determine the range of that parameter. Okay, here this is 2.8 and this is 6.5, right? And the P3 minimum value is this, right? Here 18.2, right? And here the maximum value 3.2 and maximum value 7.5, and we just find the P3 maximum value is 24. Okay, all right, so let me get that here, maybe make it smaller, right? Perfect. So you can just consider we have this. You can just consider we have this, right? Okay, we have, what do we have? We have some LTI where parameters are appearing linearly, right? Not non-linearly, linearly, right? Or affine here. Okay, and we have the parameter ranges. Okay, and after that what we need to do is basically decompose that a of p, right? Here this is a of p, right? Okay, and if you look at this a of p, these are equivalent, right? Okay, this is -1, here -1, and p2, right? p2 appears only in one place, right? -2, right? Okay, and let's check p3 in only one location, right? It appears only in one location. -1, here -1. All right, and the other ones, I call it 1 times the matrix, right? Here 1 1 -1 -1, right? The other terms. Okay, all right, let me make it okay. And here I'm going to call this AP1. Okay, I'm going to call this matrix AP1. Right, this is something that we know. This is some matrix, coefficient matrix. Okay, its entries are just numbers that we know. Okay, it is not something that we optimize or something, right? Okay, and here I'm going to call it AP2, and for this matrix AP3, and for this matrix A not. Okay, all right, A0. All right, since we have 3 parameters, right, we need to okay, for example, in that case there are 2 parameters and 4 vertices, right? Okay, how did we reach to that number? 2 to 2, okay, is 4, right? All right, for example, how many vertices does a cube have in 3 dimension, right? 8, right? Okay, it is the same logic. I mean, right, since we have the intervals, right, and the parameters are, they're independent of each other, basically, we consider that we need to look for every vertex of that geometric object in parameter space, basically. Okay, and all right, now I am going to call. All right, now we just define that, right? All right, we just define for numerical matrices. All right, and all right, since we have 3 parameters, I just use this function. It is decimal to binary, right? I just printed from 0 to 7, basically 8 numbers, right, in decimal format, right? And here we can see just this is just 0 and this is just 7, right? Okay, why would you do that? I mean, I did it because let me delete that. There is a purpose. I feel like you're estimating why I did that. Okay, here we need 8 matrices. Okay, 3 parameters. We need to determine or compute, basically, right? 8 A matrix. Okay, matrix, and I'm going to call them, use that type of notation, A. Okay, I'm going to use that notation, A underscore 1. Okay, and this is for, I'm going to write all of them actually. Okay, we have 3 parameters and therefore we need to basically compute 8 matrices. Okay, I just written down like this and I didn't anything actually, right? For example, all right, we just created this array, right? And okay, one by one we are going to do that. Just copy and paste, right, like that. By the way, notice I just only written P1, P2 and P3, but not the max and min values of. Okay, for example, the first, what is the first one? 0 0 0, let me write 0 0 0. Okay, and 0 0 0 means P1 minimum, P2 minimum, P3 minimum. Okay, 0 0 0. Okay, and 1 0 0 means, right, here in this case, P1 max, P2 min, P3 min. All right, I'm going to do all of them. All right, 1 no 0 here. I'm looking at this 0 1 0. Okay, minimum, maximum, minimum. All right, the fourth case 1 1 0. Okay, maximum, minimum, right? Okay, that's great. Let's check the case 5, right? 0 0 1, minimum, and maximum. All right, and 1 0 1 here, this case maximum, minimum and maximum. Okay, you need to be really careful, easy to make mistakes, right, at this stage especially. All right, 0 1 1. Okay, minimum, maximum, all right, and 1 1 1 1 1 1, maximum, and maximum. All right, and the second, come on, okay. Here in this stage we need to compute these 8 matrices. Let me remind you, we know what P1, P2, P3, their min and max values, right? So those 8 matrices, right? Those are numerical values. We know what they are, right? Okay. And in this stage, we need to construct those 8 matrices. Okay. And then now we are in a position where we have the ability to assign our, let me look at this, constraints, right? We will have some constraints, and this is quadratic stability problem, right? Okay. And the first constraint is this e being positive. Okay. And then, all right, we will have 8 v dot being negative type of constraint. Okay, 8 of them, right? A underscore 1, right? Maybe I should write it like this, would be better, right? E times a sub I. Okay, all right, a sub I, symmetric part of it. Okay, or this operator, I don't want to say symmetric part of it. Okay, and I mean I can say that wouldn't be wrong actually. All right, being negative, and here's a catch for I. Okay, and maybe let me write here for all I in, no, not 0, 1, 2, dot 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 8. Okay, all right, I'm looking at it. If we have another constraint, no, we don't have another constraint. All right, and basically this is the optimization problem. Problem, and we are going to solve this using YALMIP and SDPT3 is my SDP solver, right? And MATLAB. Okay, let's go back to MATLAB. Okay, and let me click here and control home. All right, that's perfect. Now I'm looking at the screen, and okay, this is our A0 matrix. You can check that, right? And I just, since they are those AP1, AP2, AP3 matrices are really sparse, if you recall, right? And I just constructed them in this manner. All right, here we know what P1 and P2 min and max values are, right? Okay, and then again P3 minimum and P3 maximum values, right? And here I just constructed P1y, P2y, and P3y arrays, and those arrays include minimum and maximum, the bounds actually, right? Okay, and it is a systematical way of doing this actually, right? Of course you would use for loop, but I wanted to make things explicitly as I can, right? Okay, construct the A sub I matrices, right? Okay, I ranging from 1 to 8. Okay, and why this is the case? Because we have 3 parameters, all of them has some range, lower and upper bounds, right? 2 times 2 times 2 equals 8, right? Okay, all right, again this is exactly what I write if a couple seconds ago, right? Okay, and again here this is the let me write this, the to decimal to binary 0 from 1 7. Okay, I just created in this manner, right? Okay, this is 0 and this is 7. Okay, and 0 0 0 means, right, if you, for example, 0 0 0 0, 0, 0. Okay, and here you can see them here, this point and this point, right? Here 0, 1, 0, here 1, 1, 0, right? 1, 1, 0. Okay, okay, 0, 0, 1, right? There is only one, right? Here for the convenience, right? Okay, because we just couldn't say, hey, zeroth value of that array, right? In MATLAB, the array starts from the, 1, index 1, right? Okay, there is no zero index term. All right, and that way it is very convenient for us to, iteratively do that. We would probably use for loop, right? And that will be easy, right? Since we have the array, right? We will just, yeah, use that. Okay, all right. Hopefully in the upcoming lectures, hopefully we can attempt solving or doing some stability analysis and parametric robustness analysis in the upcoming lectures. All right, so far so good, right? Okay, here epsilon for numerical accuracy. Again, the same thing, exact same thing. Okay, I just want to make things clear. Here again, construction or definition of P, right? We assign it. All right, symmetric matrix. Here we are just constructing our constraints, right? And there is one v of x in positive type of constraint. Okay, positive definite as constraints, and there are eight negative definiteness constraints, right? You can think of it that as v dot being negative. Okay, I just iterate that all the time. All right, and after that we just solve that. Okay, I'm looking at this, maybe 15, maybe 20. Yeah, let's say to 35. Okay, right, 35 lines of code, and you just do a, let me check this, yeah, quadratic stability analysis, and not too bad, right? I will say. So let's, since I made the fonts larger, it's not easy to zoom out. Okay, let's run it. All right, and yoo-hoo, perfect. We just see the successful sort. That's really great. All right, just want to see that again. All right, and let's check what our p-value is. Here p-value is this. All right, and let's check the constraints one by one. Okay, and first constraints was p being positive. Okay, and that minimum eigenvalue of p, right, must be positive. Okay, all right, and that is the case here. This is positive, and all of those matrices must be negative definite. Okay, and then maximum eigenvalue must be each one of them, right, negative. Okay, and this is negative, this is negative, this is negative, negative, okay, negative, 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 and negative. I just want to show it to you one by one. And okay, and again this is our p matrix. And if you are kind of picky about your p matrix for some reason, and if you don't like your entries to be more than 50 or smaller than minus 50, for example, you can also use this type of constraints. And right, but in other case, I mean, this, for example, you may not find a p-value like that, right? But let's see if we can find it. Yeah, we can find it actually. All right, let's see what it is. again it is all right. It satisfies all the constraints, right? Okay, here. All right, and I'm looking at this. Is there anything that I'd like to add? Okay, I'm past the time. All right. Okay. Thanks for watching. Okay, thanks for watching, and remember the references are in the description down below.